Okay, so this is question number 51 of the Fields and Capacitance homework booklet. So in question number 51, the first part of part A, you're simply asked to define the capacitance of the capacitor. So the capacitance is simply the charge stored per unit volt. That's just a definition that is in your notes and you just have to learn. And if you write that down, that gives you 1 mark. For the second part, you're asked to calculate the charge given in coulombs that's stored on a 470 microfarad capacitor when there is a potential difference of 2.3 times 10 to the 2 volts across it. Well, this is an equation that we've seen a lot. It's the basic equation that comes basically really from this definition of the capacitance, that the charge is equal to the capacitance multiplied by the potential difference. We simply take the numbers we've got from this equation, from this statement over here. So capacitance is this number. The potential difference is 2.3 times 10 to the 2 volts. Multiply those together, gives you 0.11 coulombs. And if we do that, then that gives you a second of 2 marks. So in part B, we have a 470 microfarad capacitor and it's connected in a circuit, in this circuit over here. And this circuit enables it to charge when the switch is in position S1, so when the switch is in this position over here. And then when the switch is flicked over onto this side into position S2, it's then discharged through this resistor over here. In part 1, we're simply asked to calculate the time constant of the discharged circuit when the switch is in S2. So the time constant, this T, is simply equal to the resistance of the resistor, this number, multiplied by the capacitance of the capacitor, this number up here. So we simply multiply those two numbers together. So the resistance is 3,600, capacitance is 470 microfarads. Multiply that together gives you, to two significant figures, gives you 1.7 seconds. And we remember that the time constant is given in seconds. And if we do that, that's worth 1 mark. We're then told that the capacitor is then fully charged and it's discharged. So the capacitor is charged up and then we discharge it through the resistor. We've got some axes on the next page and we're asked to put some appropriate scales on and draw a graph to show how the potential difference across the capacitor varies with time as it discharges. So there's a couple of things we need to think about. First of all, when we draw our curve, where is it starting from? Well, the very first thing we did is put a scale on here for potential difference. So the largest potential difference we're going to have is 12 volts because that's the potential difference of the battery. And so the potential difference across the capacitor can't be any greater than that. And then I decided the time that I'd look at across the bottom. Well, I know for a fact that the potential difference falls to approximately 37% after 1.7 seconds. So I decided that I'd actually go to approximately 3 time constants, and it would enable me to plot 3 points on here so I can get the curvature right, because the actual marks for this thing are a correct curvature. So to make sure of that, I plotted 4 different points, the initial point and then 3 subsequent points. The intercept on the v-axis needs to be correct, and also this becomes asymptotic to the time axis over here. So basically, right at the very end, it follows the time axis. So that's worth the second mark. And then the third mark is for basically putting on these values, so that the values after 1 time constant. So basically, I know that it starts off at 12 volts, and then after 1.7 seconds, it falls to 37% of that, which is basically 4.4 volts. After another 1.7 seconds, so after 3.4 seconds, it falls to 37% of this value, so that's 1.6 volts, which is that point there. And then I did it for the third value, so 5.1 seconds, I worked out what 37% of 1.6 was, just to give me an idea of where this particular point was. That gives me A, the correct curvature, 1 mark, B, the correct starting point, and this becoming asymptotic, so it follows the t-axis, 2nd mark, and it enabled me to put these points on here to show what the potential difference was after 1 time constant, and that's the 3rd mark. So that's 4 marks altogether, 1 mark for the graph and then 1 mark for the calculation of the time constant earlier. So in part C, we would then start to look at what happens as we charge the capacitor up. So we've got the charge against the time, and we're simply asked to explain why the charge across this capacitor changes as it does in this particular graph. So this is worth 3 marks. So the very first mark is basically for saying that initially there's no potential difference across the capacitor, so therefore the rate of charging is high. And you can tell that from the graph because the gradient is steep. The second mark is basically for saying as the capacitor charges up, the potential difference across it increases. And then the third mark is for saying as the potential difference increases, the rate of charging reduces or the rate of charging decreases. And that's your third mark. So you've got 1 mark for saying what the potential difference is at the beginning, 1 mark for saying what happens that the potential difference increases as the capacitor charges, and then 1 mark basically for saying that the rate of charging reduces. And you can see that from your graph. So the gradient shows you the rate of basically the rate of charging. So it charges up quickly here, and as the gradient goes down, then the rate of charging decreases. And so that whole question is worth 9 marks. So that was question number 51 of the Fields and the Capacitance homework booklet.